So thanks for joining the online webinar again. And my name is Ben from the EMEA. And the topic today is how to interpret the injection molding simulation results. First of all, I'm going to introduce you the simulation process. And next, I will show you how to interpret the analysis results. And in the end, I will make a short summary for you. So this pie chart introduces the fundamental understanding on the simulation process. So firstly, you need to define what kind of the modeling you are applying. Then you have to make a mesh and choose the suitable material for your model. And you need to set the corresponding parameter for your simulation. And then the last item here, you need to design analysis way before you get in the results. So finally, you can get the analysis results and read the report. So we are starting from the filling stage. So being able to analyze the filling stage, we can verify the filling performance when the part filled out completely. So from the filling analysis, we can have more understanding on the short problem and the location of the air trap and the potential wear line location and the area of the hesitation on your part and the flow imbalance on your part too. And also the pressure distribution on the part and the sprue. So melt from time is a very useful resource for us to check the short, wear line, air trap, flow hesitation, and flow imbalance. So this page shows you the example of the animation of the melt from time. And the model here is the medical box. So short is the first common problem we usually check after a part filled up. So before we check the short result, we have to understand what is the short. So the definition of the short is the incomplete filling of mold cavity, which results in the production of an incomplete part, which means the part in the mold cavity cannot fill up because of some mistake. So in our software, we can check the short result by seeing the animation of melt from time. So in this picture, you can see the left side. You can see the model with the short and the model without the short. Or you can check the short result by the filling log file. And the log file show you how much percentage of the filling on your cavity. So in this case, we can see only 90% of the filling happened on the short example here. So the other common result is the air trap. So you can adjust the percentage of the melt from time. Air trap usually occurs at the flow front end. And you also can click the air trap icon here to see the air trap press. So from these results, you can have a basic understanding on how to design your venting press on your mold. So the location of the wear line is an important result for a product because in general, the location of the wear line is the spot of the stress concentration, which means the area is easy to damage. So we can check the wear line result by adjust the percentage of the melt from time again. Or we can click the wear line icon here to see the wear line location. So we have a couple of results to help analyzing the wear line. So the first one is the wear line temperature. The definition of the wear line temperature is the two melting fronts converge together, then create one boundary line. So the hotter wear line temperature provides stronger wear line strength. So also from the statistic results, we can see much percentage of the wear line temperature is kept at higher temperature. So which means the in this example, the wear line is very strong. And the other way to check the wear line is by wear line angle. So wear line meeting angle is the meeting angle between the two melt fronts. So in general, the larger of the wear line meeting angle, the stronger wear line will be. So for the same example, we can see most percentage of the wear line angle is scattered in the larger angle in this example. So for the flow hesitation is a useful tool to analyze how the fast melting flow is growing in the cavity, and utilizing the isocontour function to show the isocontour line. And basically, what you are looking for is the space between the contour line. So having a nice uniform space between those contour line basically means to get a nice uniform flow behavior in the cavity. So if there is a big distance between the isocontour line, means the area has a flow hesitation. So it might be have the thin wall section on this part or a bunch of corner on this part. And to utilize the animation of the melt front time, we also can check if the cavity has flow imbalance problem or not. So flow imbalance problem is caused by many reasons. For the theory explanation, the difference flow length will cause the flow imbalance, and the diversity of the resin temperature in the runner are the two main reasons to cause the flow imbalance. But for the practical situation, the mode design, for example, the dimension of the gate or the runner size are the factors to cause the flow imbalance. And the modeling how to make the mesh and the mesh type will cause the flow imbalance. And the mode tooling, how to make the mode during the grinding, milling, EDM, and the assembling process. And how to set our process parameter, and also the measurement capability on your part. These factors are the reason to cause the flow imbalance. So in this example, we can see the cavity farther to the gate needs more time to fill up. So this is an example of the single cavity with multi gates. So basically, if the gate location are close to the sprue, the filling pressure is higher than the gate, not approach to the sprue. According to these results, we can predict gate 3 and 4 might have better packing efficiency than the gate 1 and 2. So pressure drop is a quantified result to illustrate how many megapart the runner or the part consuming. And it is also good tips for the part designer to redesign the runner configuration in order to get more equal pressure and get the better quality of the part. So in this example, we can see the runner consumes about 91 megapart. And after you turn off the runner, the part only contributes about 38 megapart. So the pressure drop in this case is about 53 megapart. And from the XY curve, we can look at the sprue pressure. And in the background, we can see the melt front time animation. And you can see a peak in the middle of the curve. Basically, it means the runner is filled up and the melting plastic is start to fill the part. And the spike here, it means the melting resin is filled up the one side of part and start to flow to the rest of the part. So let's move to the packing phase, the second phase of the injection molding cycle. And the physical property of the polymer material is an influence factors to the packing process. So I want a short illustration on the PVT curve before interpreting the analysis result. So this page shows you an example of the PVT curve. And in the example, the material is an amorphous polymer. We call it the PMMA. So when the resin goes through the hopper to the feeding section, which is the first section of the screw, the resin starts to become the melting phase. And the rotation force from the machine push the molten resin to move forward to the transition and the mixing section in the barrel. Then the molten resin will go through the nozzle to fill up the cavity by moving force. So this kind of the driving force will make the molten resin to fill up much percentage of the cavity. And in order to fill up the rest space of the cavity, the molten resin will be pushed to cavity by machine pressure. So after the packing process, the pressure of the cavity will drop to the ambient pressure. And then we will pick up our part at the environmental temperature after demolding process. So all we know, dimension of the polymer material is easy to be influenced by the temperature and the pressure. So from this graph, we can understand the gap between the point 6 and the point A is the volume change area. We also call it as the volume shrinkage. So how to improve the gap between the point 6 and the point A? In general, you can try to increase the packing pressure or extend the packing time, or you can try to reduce the melting temperature in your process in order to solve volume shrinkage problem. So in our software, molten core results provides the deep view to know when the gas freeze out and the effective packing time. And in this example, we can see the gas is not frozen yet at 5 seconds, which means the melting resin still goes through the gas to the gas cavity. However, the gas is frozen at 7 seconds. So this result is very useful and it can provide a prediction to save the unnecessary packing time as the gas is frozen. In the other way, you can check the prediction of the gas freezing time in the packing log file if you have selected the option before the analysis. And in this picture, you can see the packing log file provides you the prediction of the gas freezing time here. And in this case, the gas freezing time from the log file is about 7 seconds. So with the ISO surface function, we are able to look at the hot region area of the part. And by seeing the animation, we can see the temperature change through the packing phase. And to check what area is the last area to be cooled, and look at the temperature uniformity, we can predict what area might be shrinkage. So the next common result we usually check in the packing phase is the sink mark. And we can look at the potential sink mark area by a couple of results. The first one is the sink mark indicator. It's an index value to predict sink mark in a thickness different area. And the other one is called the sink mark displacement, which provides you the quantified value. So for this example, it is the medical box. And we can see the indicator value near to the gate here is a negative value, which means the pressure in this area is too much. And on the other hand, if the indicator is positive in here, it means the packing is not enough, which might lead to the sink mark. And in the example below, we can see the sink mark displacement shows on the two specific areas, the ribbon region and the seeker area, which are the two common regions to have the sink mark problem. So how to solve it? How to solve this kind of the problem? So this page shows you the smart tips to improve the sink mark issue. And for the rib region, the golden rule A is the thickness of the rib should be less than 50% of the wall part. And the golden rule B is the radius should be approached to the 0.125 times of the wall thickness. And for the boss region, the rule one is the depth of the The both should be larger than the external height by less than 30% of the part thickness. And rule 2 is the outer diameter at the top should be 2 times to the 2.4 times of the screw diameter. And you also can find a lot of information from the website, and a lot of the textbook will teach you how to improve your part. So volume shrinkage shows the percentage of the part volume change due to PVT as the part is cooled down from the high temperature and the pressure to the room temperature and the ambient pressure. So a couple of things to look forward. And typically you can see a color bar besides to your model here. If the value is positive, which means the part shrinkage. If you see the negative value in the scale, it might be some kind of the value expansion, maybe due to the overpacking. So, and the right picture shows you the temperature profile inside the part after slicing the part. So in here we can see the volume shrinkage is usually happened at the higher temperature region during the packing phase. So in this case, it's a worst case. In this case, the volume shrinkage is about 17%. So the last one in the packing phase is the clamping force. And the history curve can be found in the XY curve item under packing phase and help user to determine the required machine spec and predict the potential flash problem. So now we are jumping to the cooling phase, the third phase of the simulation. So before showing you the results, I want to spend a few time to talk about the injection molding cycle. And the cooling stage takes most of the time in the injection molding cycle. So if you are a factory manager, you will try to save the cooling time to increase your production yield. And here shows you the one series formulation to calculate the cooling time before injection molding process. And I must to say it's not 100% precise, but it can give you a number to predict the potential situation in the future. So the next things I want to talk about is the time to ejection temperature. And this is the time required to cool a part below the eject temperature. And we can look at the results by the isosurface tool. And this function can give you an idea to know what area in this part are standing with the hotter temperature. So from the static results in here, we can know how much percentage of the cavity are reached to the ejection temperature already. And in general, the suggested cool time is the time for 90 to 95% of area reached to the ejection temperature. So in this case, we can know that 6 seconds of the cooling time can make 96% of part to reach the ejection temperature. And by the way, you also can open the log file to check the ejection temperature too. So after you open the log file, you also can check the ejection temperature. And in this case, the injection temperature is about 100 degrees C. And the cooling efficiency. So we can have the quick value within the software. Not only look at the filling at a part, packing at a part, but also analyzing the cooling channel. So being able to see the cooling efficiency, what cooling channel have the better cooling efficiency. And the results can tell you how much percentage of the heat energy is absorbed by the cooling channel versus by the other factors such as the Mobius or atmosphere. In this case, we can know the lower cooling channel provide better cooling efficiency than the upper one. And the results also can provide a good tips for a designer to reconsider how to design a cooling channel in more efficiency way. And the last part in the cooling stage is the cooling temperature. And in this case, we can see the hot spot region are located to the corner of the part. And this is usually related to the cooling system design. So let's move to the last phase, warpage phase. So in this section, I would like to spend some time to talk about what is the warpage and the warpage type before interpreting you the result. And warpage is a serious problem we usually face after the part demotes to the atmosphere temperature and the ambient pressure, especially for some kind of the plate shape product. And the temperature difference between the top side and the bottom side is one reason to cause the warpage. And the other factor to cause the warpage is the pressure distribution on your part. If the part has the imbalanced pressure, it will cause the warpage too. So and for the fiber reinforced material, fiber orientation is also an potential factor to induce the warpage problem. So there are three different of the warpage types. The first one we call it linear shrinkage, which means the material is shrinkage along the specific direction. And the second one is the flatness, and you can think it as a kind of a bending, and the product usually bends to the downside or upper side. And the last one is the roundness. The definition of the roundness is how close the shape of an objective approach to the mathematical perfect cycle. So basically, you can look at the warpage displacement results by isolated x, y, or z direction here. And we also can utilize the warpage deformation tool to raise the scale in order to get a better visual face on how the warpage trend is. So sometimes one-to-one scale is hard to see the part is warping. So by able to increase the scale, you might be able to get much better visual image how the part is not only shrinkage but also warpage. So in this case, you can see the two sides of the part are warpage to the outside. So if you don't raise the scale, you even don't know which areas are having the warpage issue. So for the next slide, I would like to show you how to measure. I would like to show you how to measure the linear shrinkage and roundness by short clips. And this clips shows you how to measure the linear shrinkage and to compensate the linear shrinkage. So the first thing you have to turn on the measure distance here. And to measure the direction you want. Okay, so in this example, the linear shrinkage is about 1.9% along the y direction. And now we have to turn on the deformation function to compensate the linear shrinkage of the y direction. So if we compensate 1.25% linear shrinkage of the y direction, in here, here we can see the linear shrinkage of the model are modified to the 0.6%. And the last thing is don't forget to export the modified model. And the second clip shows you how to measure the roundness on your part. So the first thing here, you need to turn on the roundness function and then go to select the circle you want to measure. In here, you have to open the part mesh so that you can choose the circle you want. Don't forget to open the part mesh. Then to explore the roundness result, and you can check the more detailed information in the Excel file. And in here, I will show you again how to measure the roundness again. Okay, so if you use the roundness function, don't forget to see the Excel file because the Excel file can show you a lot of details. Okay, so here's a summary. With the Model 3D software, user can have a good understanding inside the cavity during the different injection phase. And the second one is depend on the simulation results, user can understand how to optimize the mold design and the part design. And the cooling time occupies the most of the injection cycle. So cooling analysis helps user to evaluate effective and the efficiency of the cooling channel layout to achieve high quality process. And the last thing is the warpage is the common problem we already know, and we usually need to solve it. So Model 3D can predict the warpage percentage along the different orientation. And the user can also utilize the compensation tool to modify your model.